In the previous section, we have been able to identify the different types of fatigue stresses and what is the appropriate modeling level to extract these stresses. Now we are going to use these stresses to estimate the amount of damage caused by fatigue. In order to be able to do the final processing of fatigue stress for final fatigue check, you need a couple of extra tools. I'll talk first about the constant amplitude extra tools that we need. Going back to the examples that we viewed at the beginning of this series, we will find out that if the main stress is compression, that increases the fatigue life and it gives you more endurance for the structure, meaning you will have more cycles to go until failure. But if the main stresses are tension, in that case, that decreases the fatigue life, and that means you have less cycles to failure. From there is an extra tool required when you are dealing with a constant amplitude cyclic load called mean stresses correction. There are few methods here to sort of correct the mean stresses to capture this phenomena. The names of those methods here are presented. I'm not going deep, I'm just scratching the surface, but if you want to dig deeper, I guess that would be a good start to begin with. The second thing is check fatigue for constant amplitude cyclic load is kind of a straightforward. You have the number of cycles under a certain stress range. If you are under the SN curve, you are okay. If you are outside the SN curve, you need to do something to bring this point under. But what is the deal with the variable amplitude cyclic loading? And then that brings us to what kind of extra tool required to further process the fatigue stresses to be able to do the proper fatigue check. So as we know that for variable amplitude, we had this example, noise load subjected to wind load. And normally wind load is a variable amplitude, which is a plot over random stresses happening over different number of cycles. From there, we can sort of change this view to a more friendly view. How's that? We believe that this random plot is a group of constant amplitude cyclic load that happens with certain stress range for a certain number of cycles. Putting them together will give us the original random plot of the wind load. To do that, we need an extra tool called cycle count. There are two methods, rainfall counting, rainflow counting, or reservoir counting. Rainflow counting, it is more suitable for computer applications. Reservoir counting is more suitable for manual application. And again, I'm not going into details, I'm just scratching the surface. And if you want to go deeper, that should be a good start for you. Okay, so using cycles counting sort of converts that random plot to a group of constant amplitude cyclic loading with certain stress range for each that happens over a certain number of cycles. The second tool that we need to sort of process the fatigue stresses from the variable amplitude is required to sort of understand after plotting these points on the SN curve, as we can see here, you got every constant amplitude cyclic loading as a point on the SN curve, but you're still able to sort of understand what is the next step. So the second tool is minus rule, which enables you to estimate the amount of damage that each point of those contributes to the accumulative damage caused by fatigue. And that's what we are going to explain in the next slide. If we have a structure with 100 years design service life, and we want to satisfy the ultimate limit state requirements for the wind load case, we bring in the historical wind record to estimate the maximum wind cost for a given probability of exceedance over a certain return period. This return period depends on the type of the structure that we are designing. The structure will be subjected to the maximum wind cost once in its lifetime, and throughout its lifetime, it's going to be subjected to a different levels of pressure, wind pressures, that changes from 0 all the way to the maximum wind cost pressure. From there, we could say that the structure is subjected to stress levels that could be represented as percentage of the maximum wind-induced stresses coming from the maximum gust pressure. And this percentages ranges between 0 and 100% of the maximum wind-induced stresses resulted from the maximum gust pressure. From there, the Australian code and Eurocode came up with this graph. So they represented the different stress levels on this graph as a percentage of the maximum wind-induced stress coming from the maximum gust pressure on the vertical axis. And in the horizontal axis, this is the number of times that that stress level is exceeded in the structure's life. To give a bit more clarity about this, if you have a stress level here, it's a certain point at the vertical axis. The number of times that this stress level is exceeded is represented by these red dots, which plotted at the horizontal axis. This graph will be a crucial or the key graph for us to use to calculate the damage resulted from fatigue subjected to a variable amplitude cyclic loading like the one shown on the screen here. So to do this, we have to use the concept of segmentation for the stresses or incremental stresses. So we divide the graph into stress increments, or we divide the graph into stress segments. Each segment represents stress increment, and each stress increment is basically a percentage of the maximum induced stresses resulted from the maximum wind gust. The segmentation, the accuracy of the segmentation is based on how much accuracy the designer needs to do. So you can go as far as 1% segmentation, 5%, 10%, whatever. So each segment of those represents a stress increment, 10% of the maximum stress, 20%, 30% of the maximum stress, and so on, or 5, 15, 20, whatever accuracy is desired. So how do we use this segmentation or stress increments to calculate the damage? We will study one segment and understand what is the process on the one segment, and that should be repetitive for all stress segment shown here. If we take, for example, this segment, stress segment. So this stress segment represents a stress increment, and it intersects with the graph at 2 points, this point and this point. Between those 2 points is the number of cycles of that particular stress increment, meaning that this stress increment, the structure will be subjected to this stress increment for a number of cycles equals to small n3. We can repeat that for different stress levels at different stress segments. So let's say for delta sigma 1, this stress increment is going to happen and the structure will be subjected to this stress increment for a number of cycles equals to small n1, is determined by the points of intersection for the stress segment with the graph itself. Let's do that again. For this stress segment, stress increment here, delta sigma 2, will happen for a number of cycles equals to small n2, and small n2 is determined by the points of intersection of this stress segment with the graph itself. You can do that for different stress levels and get the corresponding number of cycles from the intersection of the stress segment and the graph. So we end up having pairs of stress range or increment and the corresponding number of cycles. So we have delta sigma 1 and the corresponding number of cycles, small n1. We have, let's say, delta sigma 4 and the corresponding number of cycles, small n4. To represent that graphically, we can use each pair of stress range and cycles and corresponding cycles to plot a constant amplitude cyclic load time history as we see here. So this point on the graph and this stress segment could be represented graphically as we can see here with a constant amplitude time history. Its amplitude is delta sigma 1, and the length of this time history is small n1, small n1. We can repeat that for all the stress levels that we have investigated. So for this stress segment that represent a certain stress range, which is basically a percentage of the maximum wind-induced stresses resulted from the maximum gust pressure. So this time history has a constant amplitude equals to delta sigma 2 and the length of the record equals to small n2, small n2. This applies for all other stress levels shown on the screen. So the graphical representation and the end-up results will be a group of constant amplitude time histories. When they are combined together, they will give the same effect of the random stress historical record that were pulled up on the screen seconds ago. Now, we need to use this to calculate the damage resulted from the fatigue. To do this, we have to set up a few tools. First is the SN curve, and then we need damage reservoir, and we need to plot the cumulative damage and the incremental damage. We will explain each one separately. The SN curve. We need to plot the reduced SN curve. We know the type of the structural connection that we are designing, so it should be easy to specify the corresponding detail category or the reference fatigue strength. And from the method of fatigue assessment we are using, we should be able to specify the strength reduction, the relevant strength reduction factor. From there, it is easy to plot the reduced SN curve for the specific structural connection that we are designing. Now, we are going to take each pair of stress range and cycles count, and plot it as a point on the reduced SN curve. So, for the first constant amplitude time history, it is represented as a point on the SN curve. The coordinates of this point is the stress amplitude or the stress range, delta sigma 2, and the length of the time history, the number of cycles that the structure is going to go through and subjected to delta sigma 1, which here is small n1. Using this point and plot it here. And then we calculate the endurance. So the endurance is the maximum number of cycles to failure for a structural connection or for a structural detail subjected to a stress range equals to delta sigma 1. And here, Minor's rule applies. So the damage is basically equals to the number of cycles, the actual number of cycles of specific stress range divided by the maximum number of cycles to failure under the same stress range. So it's small n1 divided by capital N1. And then from there, we can calculate the damage and start to plot the first segment in the cumulative damage curve and the first segment in the incremental damage curve. So far, cumulative damage equals the incremental damage equals to D1. And we put the damage in the damage reservoir. Because the damage is accumulative, we will use this reservoir to pile up the damage as we accumulate it as we go. Now we'll do the same thing for the second constant amplitude cyclic loading. So we plot this time history as a point on the reduced SN curve, which is stress range equals to delta sigma 1, which happens for a number of cycles equals to small n2. Stress range equals to delta sigma 2 happens over a number of cycles equals to small n2. And then we calculate the endurance, which is the maximum number of cycles to failure under a stress range equals to delta sigma 2. From there, Minor's rule applies. Damage equals to the number of cycles for delta sigma 2 divided by the maximum number to failure under delta sigma 2. And then we accumulate the damage in the damage reservoir, and then we plot the cumulative damage, which is D1 plus D2 for a number of cycles equals to N1 plus N2. And then we plot the incremental damage. Same thing for delta sigma 3, and probably that's going to be a repeat for what I've explained one more time to make sure that everyone is on the same page. So delta sigma 3 happens for a number of cycles equals to small n3. Then we get the endurance, which is the maximum number to failure for a structural detail subjected to a stress range equals to delta sigma 3. Minor's rule applies. The damage equals to the number of cycles of a specific stress range, which is delta sigma 3, divided by the number of cycles to failure for a structural detail subjected to the same stress range delta sigma 3. We accumulate the damage and then plot the incremental damage, which is D1 plus D2 plus D3 over a number of cycles equals to N1 plus N2 plus N3, and then we plot the incremental damage. Same thing will happen over and over again for all the stress ranges and all the stress levels that we have investigated. Once we finish, we will find that we have been able to plot the total accumulative damage curve and the incremental damage curve for the whole stress levels, for all stress levels applied to the structure throughout its lifetime, based on the accuracy that we've chosen in the beginning. Okay. Now we get what we call total damage, total accumulative damage, which should be less than or equal to 1. It shouldn't exceed 1. Okay. Now we were using this total accumulative damage. We will have a couple of new properties for the structural connection that we are designing, the fatigue life. So we are familiar with the design service life, which is maybe 50 years or 100 years, depends on the type of the structure that you are designing. But the new property here is the fatigue life. Fatigue life basically equals to the design service life divided by the total damage. The design service life divided by the total damage. That gives you the fatigue life. Fatigue life is the ability of the structure, is basically represents the endurance, which is the ability of the structure to sustain a cyclic loading for a specific number of years without exhibiting signs for fatigue failure. The second property is the damage per year. So the damage per year equals to the total damage divided by the design service life. The total damage divided by the design service life. So each point here on the vertical axis represent a damage at a certain age of the structure. Now, how do we specify the remaining useful life of a certain structure? If we calculated the total damage, there are two scenarios. The total damage might be greater than 1, which is not desirable, or less than 1, which is the design intent and the design target. If we speak about a damage less than 1, let's say equals to 0.8. So the fatigue life equals to the design service life divided by the total damage, which is 0.8. 100 years divided by 0.8 total damage gives you 125 years. That means that the structure will live its whole intended design service life without showing any signs for fatigue deterioration or fatigue failure. But as a designers, we stick to the minimum of the design service life, which basically controlled by durability limit state or fatigue limit state, and the fatigue life. So the minimum of 125 years and 100 years is the 100 years. So we say that this structure will live for 100 years. And in that case, durability limit state controls the service life of the structure. If the total damage is greater than 1, which is 1.25 as an example, in that case, your fatigue life equals to 100 years divided by 1.25 gives you 80 years. That means that the structure will not be able to complete its intended design service life because it's going to show signs of fatigue deterioration and fatigue failure before reaching the 100 years age. So the useful life of the structure will be limited to the minimum of the fatigue life and the design service life. And in our case here, the fatigue life controls because it's less than 100 years and it's 80 years. Final note is what we call damage triple S. Simple, straightforward, and smart. If we look at the whole process from the beginning to the end, we will find that each stress range here, as we said in the beginning of this slide, is basically a percentage of the maximum wind-induced stresses. And then when we get into the SN curve, we get the damage, and the damage basically becomes a function of the maximum induced wind stresses. When we accumulate the damage, the detail category, which is a known figure, a known number, because it relates to the structural connection or the structural detail that you are using. So the damage becomes a function of the maximum induced wind stresses and the detail category for the structural detail that you are designing. Hence, the total damage, which is the accumulation of the all incremental damage, is basically a summation of functions. Each function is a function of the maximum induced wind-induced stresses and the detail category. If the detail category is given as per the structural detail that you are designing, and you do not know the maximum wind-induced stresses, which is the ULS state, the ultimate limit state wind stresses, you can get this value and estimate the maximum ULS stresses that a specific structural detail is able to sustain to satisfy the fatigue requirement so that damage do not exceed 1. So all what you do is to equate the total damage with 1. You have only one known in this equation, which is the maximum ULS wind stresses. Once you do that, you will get a formula that relates between the detail category for a specific structural detail and the maximum induced wind stresses that this structural detail can sustain. This is a universal equation and it applies for all the detail categories.